Hello, hello and welcome to this video. In this video, we will learn about B plus trees. Last video was on generic data structures, and before that, we did B tree. I did not explain the code of B tree. The reason was I was going to spend a lot of time on B plus trees. So there will be two parts of it. This is the first part. This will cover the theory and a bit of visualization. In the next part, we will look at the code and try to understand by going in depth. Since it will make a long video, if I make one video, therefore I have decided to split into two. So B plus trees are much like B trees. That is, they are efficient for anything where you need to find data on disk. For example, you can have databases or file systems or large scale SAN NAS systems. So once your data does not fit in RAM, the data structures like arrays, linked list, and binary search trees become inefficient due to excessive disk operations. So to accommodate for these downsides of the arrays, linked list, and binary search trees, B and B plus trees were developed. Okay. A B plus tree is a self-balancing multi-level search tree that maintains sorted data and allows searches sequentially access, insertion, and deletion in logarithmic time. It is a variant of the B tree and is particularly optimized for systems that store data on secondary storage devices such as hard disks and solid state devices. Today, B plus trees form the backbone of indexing mechanisms in most modern database management systems and file systems. I would like to add one point here. For example, if you take traditional RDBMS like PostgreSQL or MySQL, they will make use of B plus trees to create the index. But if you take distributed databases, particularly distributed SQL databases, for example, you take Google Spanner or CockroachDB. I don't know about Google Spanner, but it's a clone. CockroachDB is a clone of Spanner, and CockroachDB makes use of LSM tree, log structure merge tree. So I expect that Spanner would also use LSM, that is log structure merge tree. We will look at log structure merge tree later. So log structure merge tree is another alternative to B plus tree for database indexes. Now the motivation is, as I said, that when you have to access data from the disk, the complexity is not determined simply by big O, because the disk access is much slower than the what CPU does. Okay, reading or writing from disk is orders of magnitude slower than accessing data in main memory. That is also true for disks like NVMe disks. Even though NVMe disks are very fast, the access is much slower than main memory because memory has also improved. Right now, I believe DDR5 or DDR6, 6400 megahertz is there. So as disks have improved, the memory has also improved. So the ratio of time needed to access data has moved a bit in favor of disk, but is still very slow. Binary search tree, when balanced, have high tree heights when handling millions of keys, resulting in many disk reads per search operation. B plus trees overcome this limitation by allowing multiple keys per node, reducing tree height, ensuring the tree remains balanced at all times, organizing data to align with disk block sizes. As a result, a B plus tree with millions of keys often has a height of only 3 or 4 levels, leading to very efficient data access. Now we look at the properties of the tree, B plus tree. Now there should be B plus written here. Point number one is that all leaves are at the same level. Point number two is the root has at least two children unless it is a leaf. Point number three is that keys within each node are sorted. each node except root can have a maximum of m children and at least m by 2 children. Each node can contain a maximum of m minus 1 keys and a minimum of m by 2, that is a ceiling of m by 2 minus 1 keys. Leaf nodes are linked to support sequential access. So if you look at application, then we have already discussed the SQL devices, databases. Then there are other software, for example, Elasticsearch, that can also make use of B plus tree. So the general uses is the indexing of columns in databases. So what it gives is fast equality searches, efficient range queries, because all the nodes are at leaves and they are sorted and they are linked together. And then you have index-based joins. Certain file systems also make use of B plus tree to maintain metadata, directory structures, and free space. Those, for example, these databases can be, file systems can be NTFS, ext4, and XFS. So Windows user would know about NTFS, and Linux users would immediately recognize ext4 and XFS. So B plus trees are used in storage engines and key value stores to maintain ordered keys and enable efficient scans. In live databases, B plus tree enable multi-level indexing, allowing massive tables to be searched with minimal disk accesses. Analytical queries often involve scanning large ranges of data. The sequential access capability of B plus trees make them especially effective in data warehousing environments. Now, if you look at the structure of a B plus tree, it can look like this, okay? So at root, we have keys 30 and 60. This is not data, okay? This is the keys. And the left child would be less than 30, so 10 and 20. And the mid child would be between 30 and 60, so 40 and 50. And the right child would be greater than 60, so 70 and 80. And between 10 and 20, if you see, there is 15, okay? And between less than 10 would be 5. If there was 25, it would be over here, okay? And similarly, 35 is here and 45 is here and so on. So you can see the structure, how this has come out to be. So with this, the presentation ends, and last video, we will look at the visualization, that how insertion works. If you understand insertion, then deletion would be just reverse of that, okay? And search, we will see when we look at the code. Search is quite straightforward. The difficult part is the insertion and deletion. So let's say we insert 0. So it will, and our degree is 4 here. So this node will come, we insert 10, it will again come here. No, I want to delete 10. I don't want 10 here. I want to insert 100. And then we will insert 50. Oops. Oh, right key. Then we insert 50. So see, now there are 3. And then we will insert 25, which will cause the node to split. Okay. So it will split, and now all the values are at the leaves, and this is our key. Now we insert 40 and we insert 10. So this will again cause the left node to split, and key will be in, there will be another key in the root node. Okay, so now there are 2 keys in the root node, 25 and 50. Okay, now we insert 20. So again, if we insert 22, this will split. Okay, you see it splits, and another key is added at the root node. So this is how it behaves. So you can go ahead and insert more nodes to understand how this actually works. All right. So with this, I will end this video here, and in the next video, that is after 5 days, rather, yeah, on the sixth day, including today, or after 5 days, there will be another video on B plus tree, which will be the implementation of B plus tree. We will go in depth in the implementation because I did not go in depth in B tree. Okay, I can apologize for that. I feel bad that I did not explain B trees in full detail. But to compensate that, we will go through the code in a lot of depth. So I hope that you're enjoying this series of videos on data structure algorithms and finding it useful for your classes, for your jobs, or even for interviews. So stay tuned for more videos, and if you have not subscribed yet, make sure that you subscribe to the channel. Give the video a thumbs up because it matters to me. I feel good when people like and interact with me. If you have anything to say, make use of comment box. If you think that I have made any mistake in the video or I can improve the videos, then please suggest the ways in comment. Note that I work as a single person. I don't have a production team. I don't edit the videos at all. It's all raw, one shot recorded videos. Okay, and I do not prepare beforehand. I just take the material and it is spontaneous uh, work which I do. So the slides and all, yes, I make, but in general, I don't use a transcript. So there are always problems or hiccups in my videos. So once again, I will thank you for watching the video. Happy programming.